All right, hello everyone. So this is going to be our second lecture on machine learning, and today we're going to tackle classification. So the packages that we're going to need this week are, as usual, we're going to need tidyverse. Um, we're going to need a new package called tidymodels, which is kind of like the tidyverse implementation of machine learning models. And then we're also going to need a package called Ranger, which I'll talk about in a second. Okay, so um, yeah, we'll have those all loaded up. Very good. Um, so one thing, the data set we're going to be working on is going to be another one of these like built-in data sets. So it's called Iris. Um, so we can take a look at Iris and what it is. It's about 150 observations. And we have, oops, we have 5 columns. So this is actually a data set about flowers. This is a very old data set. I think this is kind of like from the 1920s or 1930s, and it was kind of like one of the first data sets where someone did a statistical analysis on classification. So the outcome variable that we care about is the species. It's this categorical variable. And then we have these different features of the flower, which will presumably help us classify which species it is. Okay. All right. Awesome. So that's the data set. So, like I talked about in class, um, one thing that's different about machine learning right from the get-go is that we need to take this data and we need to split it into training data, which we're going to use to actually fit the model, and then test data, which is what we're going to use to evaluate the performance of the model, its ability to predict on data that was not used to actually estimate it. So first thing we actually want to do is mutate species so that we make sure that it's a factor, okay, and not just like a character. All right. And then we're gonna do our splitting into training data and test data. So the first thing we need to do is do this thing called set the seed. What does that mean? So when we split the data, we're going to do it randomly. So we're going to take a random 80% of the data and make that our training data. However, when we do our code, we want all of our results to be completely reproducible. And if we do a random 80%, then it's not going to be reproducible because someone else who runs it would get a different 80%. That's why we set the seed. That means that whatever randomness we do, however we kind of randomly select, by setting the seed, it's actually going to exactly reproduce every time. So that's good for reproducibility when we're doing something that involves randomization in our code. So we're going to kind of initialize this split where we feed into this function, initial split, the data, which is iris, and then the proportion of the data that we want to keep as training data. Typical amount is 80%. So that's what we're going to do here. And then we have our training data then that we can access with training. And then we have our test data, which we can access with testing once we apply it to this iris split. Okay. So yeah, let's take a look here. We've got iris train, and that's 120, so that's 80% of 150. And then we have iris test, and that's our remaining 30. Now I'm getting these numbers 120 and 30 by looking down in the console and just kind of seeing the count of how many rows are in each of these data sets that we created. Okay, so we have our trained data, we have our testing data, so now we can fit some models. So the first model we can fit is a simple decision tree. So what's going to be our code? We have our model specification, and we're going to say decision tree. And one thing we want to specify is that we're going to be doing a classification problem. We know that decision trees can equally apply to like a regression style problem, like we kind of saw in class. So here, what we want is mode equals classification, as opposed to say like mode equals regression. Okay, so that's our model. That's kind of new, right? We're not just running a linear regression. We're kind of like initializing the model. And then we need to actually fit the model. Um, so we're taking model spec and we're feeding it um, the following function. So one thing that we could do is just use every um, variable when we're running our classification decision tree model. Um, and we can specify every variable in the usual way by just including them all. And then data equals iris train. However, and this is kind of how you should do it in the assignment because you're going to be using, a few subsets of the variables. Yes, you could run this, but there's an easier way to do it. If you're including every single variable in your data, instead of including all the names, you can just do dot, and that will say we want to fit this outcome to every other variable that we have. Okay, you can do it like that, and that's fit the model. Okay, so we want to assess the fit of our model. So we're going to do a few things. First of all, we're going to specify which metrics do we want to look at. We want to look at accuracy, and then we also want to look at precision and recall, which we learned about in class. Awesome. So in order to kind of assess our model and figure out how well it's performing on these metrics, we actually need our model's predicted classifications. So the way that we kind of get our classifications is with this function predict. So we predict model fit. We say the new data that we want to predict on is this test data, right? So if we were to run this, we can see we get a tibble 30 by 1 in length where we're predicting the classification. So it's outputting these different kind of flower species. But one thing that we want to do, because we want to compare these predicted values to the actual true values that are in the new data, what we can do is actually take this output, this prediction, and then nest it inside another function, bind columns. So we're going to bind these new predictions as like a new column um, in our iris test data. Okay, so once we run this whole thing, we'll see this column pred class, so predicted class, is actually now going to appear as a column in our 30 by 6 testing data. So now we can directly compare, okay, we predict this one to be Setosa, and it actually is Setosa. So we can kind of compare how well we're doing directly. And how we're going to do it is using this metrics command where we say, okay, what's the truth? It's in the column species. What's our estimate? It's in the column pred class. And what's the data? Of course, it's this thing we just created, predictions. Awesome. So what we can see, we have an accuracy of 93%, and then we have precision of 90%, and then recall of 95.6%. Okay, so pretty good for the decision tree, actually. The last thing that we can do to kind of assess our model is use this package, which I forgot to load actually, called VIP. So VIP we can use directly on model fit. And what that's going to do is it's going to create this plot, which is going to tell us the relative contribution or importance of each of the variables that were used in the model, or each of these features, the relative importance in providing accuracy to the classification. Okay, so it says petal length is the most important, petal width is somewhat important, and then these other two, sepal length and sepal width, are not important really. Okay, so that's our tree. We can also do a forest. So let's do a random forest. So we'll call this model spec2, and our command is going to be rand forest. Now with random forest, again, we'll do a classification mode, because again, this could also be a regression forest. And then we also need to now specify how many trees do we want. We want 100 trees. And then we also need to specify that we are going to estimate this using a particular like engine. So this is a more sophisticated model than just the decision tree. So it needs kind of something in the back end, and that is this package Ranger. Okay, so Ranger is going to be kind of the engine that we use to estimate our decision tree. Okay. The last thing is to be able to create this graph like we did for the decision tree. We need to specify how are we going to compute the importance of these different features in the estimation. And we're going to do it with this permutation function. Okay. So this part here, importance permutation, you don't need that to estimate the model. It's fine to omit that. The reason we include it is so we can create this graph later on. Okay. So that's going to be our decision, or our random forest. Okay. So we can fit that. Let's model spec 2. Or sorry, not fit that. That kind of initializes the model. Then we fit the model. Okay. So we're going to go model spec 2. We will fit in exactly the same way as before, using all of our variables, using our training data. And then we're going to get our predictions. We're going to do it in the same way as before, but now we'll predict from the second model using our new data and binding it to our new data, our test data. And then we'll get our metrics once again. Now we don't need to kind of initialize this thing from line 20 where we set which metrics we want. We only needed to do that once. Now our kind of remembers, oh yeah, these are the metrics that you want. And once again, truth is the species, estimate is going to be predicted class, and then the data is now going to be from predictions 2. Okay, so we can run everything, and then we can see, okay, the accuracy is now 0.967, so about 97%. So an improvement over the decision tree where we had about 93%. And then on both precision and recall, we're doing better. So here we have just a better model overall. Okay, and then lastly, we can look at model fit 2. And here now we see actually quite different with the random forest. Petal length and width are still the most important, but now sepal length and width are basically completely unimportant. Okay. All right, awesome. So that's it. That should be everything. That is everything that you need to do the assignment for this week. Hopefully you can see training models, training these machine learning models for classification tasks is extremely straightforward with this package. I would encourage you to play around and see, because there's a lot of other models that you can try out, like, neural networks or, other stuff with names like support vector machine. Um, so, or, gradient boosting. So there's all these kind of fun things you can try out. And basically, you don't need to know exactly what's under the hood to just assess, okay, how is it performing on my specific data set? Okay, awesome. So that's everything you need, and I will see you guys in class. All right, take care.